everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker. Now in chapter 12, part 2. We're going to apply what we've learned in chapter 12 to the example we've been working on. A survey of information systems managers was used to predict the yearly salary of beginning programmers/analysts in the metropolitan area. Managers specified their standard salary for a beginner programmer analyst, the number of employees in the firm's information processing staff, the firm's gross profit margin in cents per dollars of sales, and the firm's information processing cost as a percentage of total administrative costs. Let Y equal the salary, X1 be the number of employees in the firm's information processing staff, X2 being the profit margin, and X3 being the IP costs. The coefficients are given in the table below. We also obtained the residual standard error, multiple R squared, adjusted R squared, the F statistic, and the p-value. We found in this case that the residual standard deviation is 0.9999. So what can we know about S epsilon? 68% of the residual should be between -1 and +1. About 95% should be between -2 and +2, and 99.7% of the residuals should be between -3 and +3. We can check this using a histogram of the residuals, and we see that overall they seem pretty bell-shaped. There might be slight departures from normality, but it looks overall pretty good. When we plot the residuals versus the fitted values, we notice that there could be some possible fanning and some possible influential or high leverage points. When we look at our coefficients table, we can calculate the standard error of beta 1 hat, beta 2 hat, and beta 3 hat respectively. Standard error of beta 1 hat is 0.0017, standard error of beta 2 hat, 0.0365, and the standard error of beta 3 hat, 0.0692. If we want to create a 95% confidence interval for beta 1, remember that's beta 1 hat plus or minus t alpha over 2 n minus k plus 1 times the standard error of beta 1 hat. When looking at our output, we can see that beta 1 hat is 0.0039 plus or minus. We still need to get our t value. I'll just hold that place with t alpha over 2 n minus k plus 1, and then times our standard error of beta hat 1. That is our 0.0017. All right, once we get those values, we can interpret. So using R, if I set alpha equals 0.05 for my 95% confidence interval, I have n equals 67 people in my data set, k equals 3. My degrees of freedom in this case would be n minus k plus 1, which gives me 63 degrees of freedom. I can get my t value to use for my confidence interval, which will be 1.998341. All right, and my standard error from the output above is 0.0017. So the confidence interval goes from 0.0005 up to 0.0073. All right, to interpret this, we can say we are 95% confident that the true value of the slope, let me write this as I say it, we are 95% confident that the true value of the slope associated with the number of employees in the information processing staff is between 0.0005 and 0.0073. All right, what does this mean in context of the problem? A 1% increase in the number of employees in information processing staff is associated with a $5 to $73 increase in the salary of beginning programmers or analysts, while holding all other variables in the model constant. So while holding the profit margin and IP cost constant, okay? Now, a one person increase in the number of employees may not be very helpful. So let's talk about instead 100 person increase in the number of employees. So if we do a 100 person increase in the number of employees, well, now we just multiply each of these values in the confidence intervals by 100. So essentially this confidence interval here, if we multiply by 100, becomes 0.05 and 0.73. But remember, this is in thousands of dollars. So if we move this over to make it in thousands of dollars, 1, 2, 3 decimals, that becomes 50. And that becomes 730, right? So essentially a 100% increase in the number of employees is associated with a $50 to $730 increase in the yearly salary of a new programmer / analyst, right? Assuming all other variables in the model are held constant. So what does this say? This really says that as the processing staff, information and processing staff increases, the starting salaries also tend to increase for those programmers and analysts. All right, we can continue on with this example. All right, I've put the R output here again for us. We want to say, what's the average salary difference between two firms with the same profit margin and IP cost, but a 500 employee difference? All right, so let's do firm one. Firm one, that's Y hat equals 25.5378, right? Plus 0.0039 times the number of employees, right? Plus 0.0957 times the margin, profit margin, plus 0.2163 times the IP cost. Firm two is Y hat equals 25.5378 plus 0.0039 times the number of employees. Remember, but this one has 500 more employees, plus 0.0957 times the margin, plus 0.2163 times the IP cost. So if we subtract these two, the differences between the predictions for firm two and firm one, well, this 25.5373 disappears. The profit margin disappears and the IP cost disappears. And what we're left with is 0.0039 times 500, right? And we can double check that 0.0039 times 500, that's 1.95. All right, 1.95. You can use your calculator or you can use R to do that calculation. Right? And remember that we're measuring this in thousands of dollars. So really, this is $1,950, right? So that's the average salary difference between the two firms with the same profit margin and IP cost, but one firm has 500 more employees than the other. Okay, double check and make sure you can get that. All right, let's test whether the salary increases as IP cost increases. So HO, right? IP cost is beta 3. HO, beta 3 equals 0. HA, we're going to see is beta 3 greater than 0. All right, we can calculate the test statistic. All right, so T is equal to 0.2163 divided by the standard error, 0.0692, and that's equal to 3.126. And what is our p-value? All right, we draw a curve. We have a t distribution. And here, 0's in the middle. We get a value of 3.126 for our p-value. Remember, our slope was 0.2163. Our t-value was 3.126. All right, to calculate the p-value, we can say pt, right? Because we want the probability of the t distribution. We can take 3.126. Our degrees of freedom is equal to our sample size, that's 67, minus k plus 1. In this case, k plus 1 is 4. That's going to equal 63. And then we're going to say lower dot tail equals false. And we're going to close those parentheses. Okay, so we can do this in R. Similarly, if you want to use a table or something else, you can do that as well. Okay. So we can say PT of 3.126 in our degrees of freedom is equal to n minus k plus 1. And our lower tail equals false. Okay. When we do that, we get a value of 0.0013. I'm going to copy over the R code. This is the R code. Okay, so this area right here, not drawn to scale, 0.0013. Okay, so our p-value is 0.0013, very small. Okay, since 0.0013 is less than 0.05, which equals alpha, we reject H0. All right, interpret your decision in context of the problem. We're going to say that there is a positive relationship between IP costs in starting salary while holding all other variables in the model constant. Okay, so pretty much what we have here is that there is a relationship between IP cost and salary of a programmer analyst. As IP cost increases, the starting salary of those programmers and analysts also tends to increase. Now, one thing to note, our p-value is 0.0013. If you check the p-value here, this is 0.00268. This is for a two-sided test. So that means that over here was also 0.0013. So altogether, that gives us 0.0026. That would be the p-value for a two-sided test. But in our case, we only have a one-sided test because we were testing whether salary increases as IP cost increases. So we were specifically testing, is the slope positive? So that's why our p-value is 0.0013 versus, is there a relationship between salary and IP cost? If we were testing the relationship, it would have been a two-sided test. But since we're testing specifically, does it increase as IP cost increases, then we're talking about a one-sided test. So just be careful when you read questions as to whether or not you're asking about a one-sided test or a two-sided test when you carry out your work. All right. Here is some output of the first 33 people. There's 67 total. Here's the first 33 people, and here's from 34 to 67. So this is the entire data set. So if you wanted to, you could put in this data set into R, right? You could say data gets read.csv, right? My file, right? You would have already have to tell your computer where the file was. So you can do file.choose if you prefer, okay? Data gets read.csv. And then if you want, you could carry out this R code to see what the value of n was. How do you calculate y bar? How do you calculate the sum of squares total? The sum of squares due to regression and the R squared value. So here we get 0.3841. If we check the output from the previous page, notice that the R squared value is already given right there. So you can always use the output, or you can use the formulas given in the book, and you should get similar things. Remember, this adjusted R squared is what we're going to use more often. This penalizes us for the number of parameters that we put into the model. So this says, yes, the R squared value is 0.3842, but I put 3 variables in the model. So tell me the adjusted R squared after accounting for the fact of the number of variables in the model. Okay. In general, we don't want to just put so many variables in the model that our R squared keeps increasing and increasing. So that's why we're going to use the adjusted R squared. Okay, I hope you learned something about testing and doing an example. What I'd like you to do is to try to use the same data set and see if you can get all of the output. I'll give you some more code here so you can try to fit a model. You could do fit.lm gets lm, let's say that salary follows number of employees plus margin plus IP cost, data equals data. Then you can do summary, all lowercase, of fit.lm, and that should give you the output that we got before. All right, I'm sure I'll give you more videos on R, but I just wanted to give you an outlook of what the data is looking like so far. Have a great day. Hope you learned something.